Hello everybody. I am Janani, currently studying third year ECE at SSN College of Engineering. So, as a part of my internship, I've created a EV ADAS dashboard system, that is electric vehicle automatic driver assistance system. This is basically a simulation, that is the real industry level ADAS dashboard is being simulated in this project. So here I have used STM32 Blue Pill, PiximLab and Python dashboard, that is I've created using Python. So moving on. So why do we actually need this ADAS system? Basically in real world EV vehicles, as electric vehicles, they have enormous number of sensor data which include speed, battery SOC, motor temperature, torque, and etc. But the thing is, they are giving readings, but we don't have a centralized way to visualize all of them. So most of the readings or important data to be noted gets unnoticed, and because of that we are facing several problems. So most of the real time problem like faults are left undetected, which is resulting in like several hazards. That is, before any electric vehicle blasting, we can like see, we know that when the temperature is getting too much shooted up, if we get alarm of it, we could do something, right? So basically, when everything is put up in a central dashboard kind of system, it will be easier, right? So that's the main motive of this project. So in our EV ADAS dashboard system, we'll have real-time speed, SOC, acceleration, motor temperature display, and then the collision and the blind spot detection also. That is in the blind spots. It is a region where your rear view mirrors won't show. Those regions will also be displayed in the dashboard so that you can see, and it will also say the collision, if there is a chances of getting collided, it will be giving warning also. We'll have the motor temperature display, and any faults are there, we will surely alert it in our dashboard. And then the alarm system will be like a thread alarm system, that is from advisory to critical. We'll have a live Python dashboard. So the architecture is that the sensor values over here, we are not using the actual sensor. Instead, we are just simulating them using potentiometers. This potentiometers, like by sliding the potentiometers, we can vary the voltage, right? So all the sensor values are being replaced by potentiometer over here. And the main controller of the entire dashboard is your STM32 Blue Pill, where it will be getting the values from the sensors, use ADC to convert it into digital, then calculate the necessary parameters like distance, torque, SOC, time to collision, etc. And then it will be sending it to the Python dashboard via UART protocol, where it will be sending at a speed of 115200 bits per second. So next, basically in real industry we have the sensors, right? It is replaced by potentiometer over here. The vehicle control unit is replaced by STM32 over here. The CAN bus, we are using UART protocol, and we are having the matplotlib dashboard instead of HDMI display. And instead of a real-time buzzer, we are using a normal, we're just using it like, it will be highlighted in red color that it's a warning, critical, etc. So let's talk about the phases of a project. So we have to set up the hardware, establish the core logic, and send it to the Python dashboard, right? So that is what is the main idea. We have to configure the GPIO pins, read the input from sensor, convert into digital values, calculate the speed, torque, the faults, then the time to collision, etc. Then send it to the dashboard, view it. So the phase 1, it involves the it involves the installation of the required software. So basically I've listed very less. There are other softwares also. That is main is STM32 Cube IDE for the firmware programming. Pixim Lab, it's embedded system, like online lab of just real embedded system, so it has every sort of microcontrollers present, etc. Then all the required Python dashboard softwares, that is the Matplotlib, NumPy, PySerial, Python 3 pip and all. Then in addition to this, other than what I've listed, we will be requiring VSPE, Teraterm, then yeah, that's it. So then we have to configure, like if you are having sensors, at what interval will you be getting the reading the values from sensor. So here we have assumed to be it at 100 millisecond, okay, and every 10 millisecond the EV tick will be happening, okay. Then the next phase what we have done is getting the inputs, that is PA0, PA1, PA2, PA3 are used for acceleration, brake, motor temperature, SOC, and then we are doing ADC, that is we are doing 12-bit conversion. Values will be ranged from 0 to 4095, and then the time at which these values will be taken is 100 milliseconds. So initially we had got the values from these sensors. Then calculating, we had calculated the motor torque, speed, SOC and all, and we should also set up a range value, right? Because though we are simulating, speed values can be like 500 kilometer per hour and all, technically it's not possible, so we have to have a maximum limit within ourselves. So we are giving the speed like between 0 to 200 kilometer per hour, SOC and all the ranges, like what is the values it should be there. Then the feature of regenerative braking, that is when the brake applied is greater than 5% of the actual speed, there will be negative torque, which will result in the EV battery charging itself. So this is the main positive aspect of having EV vehicles, right? When you put brake, it starts charging on its own. Then our next phase includes calculating the fault values. I mean the values which are responsible for telling if this is if a fault has occurred or not. We'll be calculating the time to collision, and if the obstacle range is less than 50 centimeter, we will give the first fault. Then if it's less than 20, FCV critical, that is front collision warning critical. Then BSD is blind spot detection. If sideways, if you get any car or any vehicle coming which is less than 30 centimeter and its speed is greater than 20 kilometer per hour, then this alarm will also get activated. Time to collision, this alarm gets activated when the time to collide is like less than 3 seconds, it will be warning. Less than 1.5 seconds, it will go a critical warning. Then we have this fault itself, we have totally 5 faults. That is the motor temperature greater than 90 degrees Celsius, SOC less than 2%, collision, those collision things that we saw earlier, and if there's UART timeout, ultra sensor, like sensor values are not getting updated properly, we'll have these all faults. So basically, main reason of having this is that in most of the electrical vehicles, the problem that we are facing today is that bursting of the batteries, right? Most of the time they burst due to excessive heating, getting overheated. But if the person gets realized that the battery of the vehicle is getting overheated, like prior to reaching its maximum extent, then surely some of the misfortunate things that happens can be avoided, right? So that's the main reason why we have all this fault detection things, okay. Then the dashboard where we will be displaying everything, okay. And now we'll move on to like the actual demo. So in our ADAS, we'll finally be having all the current speed, the history of speed, the state of charge, and what mode the driver is driving, parking mode or what, and then we'll have the bird eye view of our car along with other vehicles. We'll have the then what, we'll have all the warnings and all. So let's see. Okay. So first we'll go to STM32. Over here, see, STM32 Cube ID is the brain of our project, right? So initial phase includes configuring of the IO pins. So you can see this PB8, 9, 10 and all are LED. This UART one transmission and receiving. This is for transmitting the calculated data to the Python dashboard at 115200 bits per second. The ADC input values will be given inside in PA0, PA1, PA2, PA3. If you see PixSim lab simulation, you can see it very well that they are all the potentiometer inputs. See here, PA0, PA1, PA2, PA3. Potentiometers are basically analog. They give analog outputs. Inside STM32, they get converted to digital values and we do further things. And this other output is other output input pairs are the ultrasonic sensors. Like we have a trig and echo pin, right? So trigger pin is an output pin and echo pin is a input pin. Okay, so the main.c is the main.c file which has all the function, which has see all the headers, everything, and all the .c files. It will be having all the functions called in a particular this one. It is like the scheduler when to call which one and all. In sideways you can see you have we have inc and src, and over here you have all the .c files and .h files. So the main reason of separating .c files into all separate things is that so that we can if there's any error, we can go to that particular file and check it out. The debugging state will be easier. So ADAS, this will have all the it will have the function to calculate all the parameters which are going to be visually shown in the dashboard. EV control, all the EV control parameters. Fault.c will have the time to collision controlling formulas, functions and all. Then your ultrasonic sensor, ultrasonic.c will calculate the distance from the ultrasonic sensor, like the values. This is the respective .h files of all the .c files. They are the header files. Yeah, so basically we have this PixSim lab. Here we have the blue pill, right? Now this is the entire spare parts that are added to this blue pill. So you have three ultrasonic sensors, front, left, right, trig pin PB0, PB1, PB2, PB3, PB4, PB5 respectively. And these are the respective LEDs that I have told, out of which only this 4 is active: PB8, PB9, PB10 and PB11. This is for the buzzer. You have the potentiometers over here. This is the virtual terminal. Virtual terminal shows output like this. Okay. In order to see, this is a front one, right? Let me say if the front becomes soulless, then the collision will be occurring, right? So the respective fault LEDs are getting activated. That's that. And then this is all about the PixSim lab. So how to load is that, see, when you build the STM32 C file, you would get a binary file loaded. You have to change in properties so that a binary file will get generated, and in the PixSim lab you have to go file, load bin, and then load the binary file. After loading only you will get the values in the virtual terminal accordingly. Basically in virtual terminal, what is the drawback is you cannot type any input, you can only see the output. So we have something called as term. In Tera term, setup serial port, I'm putting it as 115200. Okay, here you can actually calculate the, I mean, you can give input also. This is also same as virtual terminal, but you can give input like help, reset and all. So that's the main reason why virtual terminal is there. And another thing is that your Python dashboard as well as your blue pill both require com ports, but we can't like connect both of them in same com port, right? So you need to pair both of them. So this, for that purpose, we have this VSPE, which virtual serial port emulator, which will pair com1 and com4. Okay, it's pairing both. You can see in the Tera term that Tera term virtual terminal is in com1, and this Pixim lab, you can see in file configure, see it's com4. Okay, and now open the command prompt. Go to the folder where your evdashboard.python is saved. So over here I type as python ev underscore dashboard dot py. So I'll get the live ones. See, you can see the speed history. You can see the current speed. You can see that the time to collision is like, it's not so much. The vehicle is like so far ahead, and we will try to change the parameters in the Pixim lab. But the thing is that the values, when we change, it is like taking so much time to get reflected in the dashboard. So let's wait for some time until this vehicle comes, like so front. Speed is constantly decreasing because I had decreased in that Pixim lab, right? So it's decreasing and now it's increasing. You can see advisory alarm. So this is the overall dashboard. Thank you.